For 5 minutes before the end, should I show you? Or?
Yeah. Yes.
Okay, cool.
You have to cut me now.
Okay, welcome everyone. I'm really looking forward to Paul's presentation on using graph databases for history analysis and visualization. And the stage is yours, Paul, and I'm really looking forward to the talk.
Thank you. Well, thank you for having me again this year in the Graph Dev Room. I'm really happy to share with you our experience in using networks in many different means to study 18th century French trade. So I am Paul Girard. I am part of the Media Lab of Sciences Po, which is a research lab dedicated to digital methods in social sciences, to make it short. And I worked with Guillaume Plic, who is in the room and who will be talking tomorrow in the JavaScript room about memory structure. And we should see that. And we've done this work through inside of a research program called TOFLIT 18s, which has been financed by the French National Research Agency, ANR. So first, I will tell you about what is 18th century French trade and what is interesting. So basically, France, as a state, has started to compile statistics about its trade since 1716. Yeah, well, the Bureau de la Balance du Commerce did that. This is the organization who actually wrote reports about what were imports or exports of commodities from France or to France from foreign region. So basically, we have in French archives, in many different French archives, we can find those volumes, archival volumes, which describe trade at that time. This is what those volumes looks like. So it's a handwritten paper. Basically, it's an account book where you have goods, products placed on the earth, and we have both information like volumes and price. I'm going to tell you how and why we used network technologies in plural to create a research instrument based on the transcriptions of those archives I've just showed you a picture of. So basically what we mean by a research instrument is to be able to explore visually what was the French trade at that time. So our corpus, our data, is composed of more than 500,000 yearly trade transactions of one commodity between a French local tax CD and to or from a foreign region, country. So we have all those data along the 18th century. So we have our data resolution in time is yearly. We have those flows, right, between French cities and countries. We have 547,000. And then we had to design a classification system to reduce the heterogeneity of the commodity names. What do I mean by that? Well, this is the top 50 products names that we can find in the source volumes. It's only the top 50 on 55,000 different names. If you look at that, we have one issue, first one, which is autographic clustering. So we have huile d'olive, olive oil, written normally, and then written with semicolons just in the middle. I will talk about these semicolons later in my presentation. So we would like, actually, when we analyze the data, those two to be in the same category, please. The second kind of categories we would like to create is like more likely thematic clustering, where, of course, we have eau de vie, liqueur, and bière. Okay, sorry about that. It's in French, and it's in Old French. So it's basically alcoholish drink stuff, right? And we would like to create this category. So this is like more a thematic issue. To tackle those two issues, we had to design a classification tree. So it's not one classification, it's a tree of classifications. Why it's a tree? Because we need a hierarchy of classifications, because we need progressive aggregations. We have the sources, and then we want to aggregate a little bit, then a little bit, then a little bit, and maybe you want to stumble upon like 5 categories because you want like product you can eat, product you can burn, all kind of stuff. But we also want concurrent classifications because we want to be able to work with alternative ways to aggregate these informations. Because, so basically what I showed you is our classification tree. So on top of it we have the source. Then we built an autographic normalization classification, which rule is really simple, it's like same word, different spelling. Then we have the simplification one, which is like different words, same meaning, we put them together, right? And then we have a long list of sisters classifications. They are all based on the same root parent one, simplification one. So the simplification one has been designed to be generic, right? But the other one are thematics. So they are really bounded with a research question. And so thematic classification are, for instance, medicinal products, which is basically, we want to be really fine-grained descriptions of what kind of medicinal product we have, but all the rest can be in not medicinal products. So it's like really finely tailored classification on one specific theme, subject. So we have medicinal, we have Hamburg classification, which has been designed to make a join with another classification from another research team in Hamburg, well, targeting Hamburg trade. Canada is about, I will speak about that later, is about which goods were traded between France and Canada, and so on and so forth. So our research instruments provides, our goal is to provide exploratory data analysis tool to economic historians. Economic historians are scholars who are either historians studying economy or economic people studying history, right? So, demo time. So that is the tool online. Well, actually, this is my local version because I'm not crazy. So basically, let me just show you classification first. So if you go into classification, you can choose products, and then from there, I'll start with autographic normalization. So here you can see like cuir de bœuf. Maybe you can see, yeah, you can see, maybe. You have different spelling, Maurice Séché, Maurice Sèche, we have different spelling, okay? So this is the sources, and we aggregate them into one, like 65 different versions of cuir de bœuf tanné in sources that have been aggregated into one group into autographic normalization. And then we can also have a look at simplification. And here you can see that, for instance, grain froment, we have 23 different items in autographic normalization, right? We are getting one step, which aggregates much more different ways to talk about grain froment. We have blé millet, blé froment, blé de froment. So it's not only orthographic differences in the same words, it's different words, sorry, talking about the same thing. So if the question will maybe stumble upon your mind, how did we did this clustering? The answer is by hand. Thanks to Pierre Gervais. And then we can also have a look at the Canada one, just for fun. Oops, yeah, Canada. So basically we have 4 different categories. It's like, it's not a Canadian product, it's definitely a Canadian product. It's maybe a Canadian product, and we don't know. And the funny part of this is that you can also use this classification system to actually check if the guy actually wrote this classification did the thing right. You can do that by choosing that you are going to project the Canada 4 categories, not on the simplification, which is just the classification parents, but to the root, to the sources. So here I have all the different versions in the sources that are definitely Canadian. And you can then check what do we can go back to the source, which is for historians very important to check how aggregation has been made. That's mandatory to do research in a way. So based on source classification, we can then leverage a lot of different exploratory data analysis tools like that one. For instance, here it's simply how many trade flows do I have by year on the different direction being the point of trade in France. So we see that on top we have Marseille, But we also Nantes, which is very important. The order sort here has an issue. There is a GitHub issue on that. But let me just show you if I can filter. I just want to project on this only the definitely Canadian products. And now we can see that actually the order changed. The more important direction place for France, trading with Canadian or trading Canadian products actually, is La Rochelle in number of trade flows. So this is kind of a hint, but we can go further because we have time series. Oh, actually, so it's a Redux application, and the state has been kept. So I actually have the choices I made in the filter while preparing the demo, which is quite nice. So here I use those filters to show you two curves. One which is only Canadian products with La Rochelle. This is the brown curve, the black curve. And the purple one is the same thing, like only Canadian products going through Marseille, which is another big, really important port in France. And as you can see, we have a date here in which the curves flips. So La Rochelle is upper Marseille for all the first period and then goes down under Marseille ones, both in terms of number of flows and value of flows. And this year is specifically the year when France actually lost Canadian colonies to British Empire after the 7 Years' War. So this is the kind of analysis, exploratory data analysis, we want to provide to economic historians. So that was the demo. Sorry again for my voice and everything. One important point, what I just told you about Canada, actually I have a talk, a paper about this, much more precise, that I submitted to a conference called Digital Humanities, which will happen in Rotterdam in 2019, sorry. But this paper is under review, so maybe I hope to tell you this story later. So actually to do this, we used a graph database, Neo4j, to modelize our data as trade network where trade flows are edges between trade partners. Why? Because trade flows actually form a network, and we want to be able to dynamically aggregate flows by any classification, as I did in the demo. I want to be able also to change the classification without having to reindex my data. Because, and the last point is because we used Neo4j before, and with pleasure. You can see a previous talk we've done in FOSDEM 3 years ago. So this is our data model. So basically on this, we have the flow node in the center, and this branch is how we aggregate country names through our classification system. This branch is about how we aggregate products through our classification system, sources, operator, and direction. Right. So till somewhere in 2015, 2016, we stumbled upon a lot of Cartesian products while trying to query our Neo4j graph. We were not very clever, and we didn't have this really nice feature in the Neo4j Explorer, which show you when you do stupid stuff. But we finally stumbled upon a solution till November 2016, the 23rd. So this cipher query is basically very bizarre. So what I do here in the first match, I just want every products which are Canadians. Then I want every flows which are with those countries, these countries. And then here I'm using index of nodes to select my flows. I collect products, I collect countries, and then as developer, I actually use index inside the flow nodes. That's bad. because our specification was to be able to change classification without having to reindex. Our thing is like here I'm using indices that are in the node properties. So this not that good solution implies to index the product names, the node products value inside the flow nodes, which means that I just like use indices in the nodes, not to have to do the traversal. Okay, that's only at the source level, but still, that's an issue. And it's a bad workaround, as I just said, leveraging Lucene indices hidden inside Neo4j instead of using graph traversals. That's not good. And the problem was what? The problem was our flow node. We couldn't go through the flow node. When we were doing this, we had Cartesian products. That's bad. This flow node is actually our top degree node in this schema. That's the central point. If you want to use classification to go there in the flow and use another one there, you have to go through it. We didn't find a way. Till I realized that what we needed, what is this node? It's actually an hyperedge. And once you have this keyword and you look for information about Neo4j and hyperedge on internet, okay, you have to really want to find it. But you can find it. And it's here. And so if you open this, well, this is the hyperedge documentation of Neo4j. I read that at that time. And when I read that, I said, what? Actually, I'm just freaking stupid. So I learned this. I learned how to use it on November 23rd, 2016. And why? Because I was preparing a proposal for Graph Dev Room 2017, which I finally didn't submit because I felt really stupid. And this commit actually archived this moment of glory, of revelation, because we changed all our query planner using hyperedge. What is hyperedge? It's just, just have to do it right, basically. So basically you do a match, and your match has to declare whole the route to the central hyperedge flow nodes. And you just pile them. I want a special direction in France, Nantes, and I want all the flow with them. I want one specific classification of products and one specific item, exclusively Canada, and I want all the flow that match this. Once you've done it, like, of course. I want all the countries that are in this classification, and I want only those sources. Voila. And in the where, you just put the params of your match. Et c'est tout. Okay, actually an index-based memory structure like Elasticsearch would have done the job, actually, because we didn't have time to implement classification and modification user interface. So our main feature, which was so important, not to have to reindex, was really crucial because we wanted the user to use our web application to change the classifications. So we didn't want to reindex because of users' actions. What you can do with the Neo4j database, because you just add nodes or remove nodes in the classification part, not in the flow part, which is the source. Actually, we didn't code this user interface, but we should one day. Actually, modifying a parent classification implies to update its children. I have a tree of classification, so if I modify the root, everything underneath it has to be rewired, because I can have new nodes, new names, I can change the name, it's a mess. So together with Guillaume, we wrote an already sacred algorithm, which it will be very difficult to explain, so I will not. And this algorithm has been designed to automatically rewire the tree using set theory. Yes. Voilà. Okay, last part of my talk, and I have 10 minutes to go, so that's good. We did all of this because we wanted exploratory data analysis. So let's talk about this. So we are using JavaScript technologies. Decipher, I will talk about it just later, is a piece of software from Guillaume, which allows you to build Cypher queries in JavaScript, Beast queries. We use Express Node web framework, web application framework, but we're surrounded by Dolman, another lead from Guillaume. Graphology, it's a network statistical JavaScript library. We heard about it 2 or 3 talks ago. React for the UI, but React with Baobab as a state machine. Baobab is like Redux, but before Redux, by Guillaume again. And Sigma. Sigma is JavaScript technology to do network visualization. We've talked about this 3 talks ago. So thanks to Guillaume and Alexis Jacomi, who actually wrote all the Baobab, rewrote all the Baobab parts and React. Decipher, just a word, this is when you need to actually create in JavaScript a complicated and dynamically defined query, Cypher query. It's just like you have queries, you can put params, you can put end and push and everything, and then you build and you send to, this is a long code. You don't want to do that, right? But sometimes you have to. And then you do that, and then you do that, and then you do that, and then you database Cypher query build, right? That's really cool. If you are in JavaScript and you need to do Cypher, you use Decipher. So to sum up the technological part of the talk, we basically homebrewed open source data science tools, thanks to Guillaume. And so it's on our GitHub. And soon we will also release the data on a data package format. So Graph Model is not only a convenient way to store and query our data, but also a powerful visual object to explore French trade geographical structure. So here I'll tell you how we used network not only to store data, but to analyze them and visually. So I will not have time to do the demo. So this is a picture of what you can achieve if you select these filters on our website. So this is the locations database in which you have a bipartite network where you have 2 types of nodes. The first one is point of trade in France and point of trade outside of France. And then the question here is like, why didn't we use the geographical layouts? I mean, all those nodes are actually placed. First, because then you need to geolocalize everything, and we have points like north. That's an issue because in history we don't really have necessarily precise or stable level of precision of data. So that's an issue. That's the first one. But more than that, and also it will require for us much more work. That's another important part. But the last point is that the excuse we use for the 2 first one. The excuse is that actually when you have a network of flows on a geographical map, if you put the nodes precisely on the map, you will not see the network structure. You will only see the geographication spreading of your points. That's an important information, but you don't see the structure. You see the geographical layout. And what we wanted to study in our, to let our users study is more likely how the trade networks, the trade flows actually change the geographical layout to show what is the trade structure, geographically speaking. For instance, here, okay, Marseille is close to Italy. Okay, yes, of course. But then you can see that Holland is a very important partner for quite all of France, not only north part of France. Okay? This is basically something I stumbled upon on Twitter recently. And actually, just to show my point, it's a geographical map with a network. and then the maps is distorted, yes, by the network structure. That's exactly what we want to do, to see how the geographical layout is actually modified by the links between the places. So that's not from our team, right? It's a shifted maps from those guys, Till, Nagel. Well, there is a link to the paper here. Second network analysis we've done is trade projects specialization patterns. Okay, I'm going to have to be quick. So if you have a look at the sources, you see a lot of semicolons. I showed you one before. So semicolons actually represents handwritten accolade brackets that have been used in the sources because they wanted, the people who were writing those reports who wanted to spare time and ink, right? By using those brackets, by using a general specific aggregation system. So they will write wine, a huge brackets, and then from Burgundy, from Bordeaux, from, right, generic to specific. But two issues. First, manual transcriptions, we did, and 18th century reporting practices, those guys at that time did. Those practices of writing were not applied equally. Writing practices are never applied equally, in my experience. So we decided to replace semicolons by some glue words when aggregated product names in our autographic normalization classification. But we compute actually a product terms co-occurrence network. So we take a name of a goods like vin de Bordeaux de très bonne qualité. So it's like wine from Burgundy of a very good quality. We remove the off, the from, everything, and then we put a link between the first word and the second one, between the second and the third one. So it's not exactly a co-occurrence network, but almost. The code is here. This is where we use graphology, actually. And this is what you output when you look at, this is our network of co-currencies of trade from La Rochelle, exports from La Rochelle between 1720 and 1729. And what does this network tell you? Even though we used a classification, the simplification here, by doing these networks, we just provide you a clustering of terms which compose all these trades. So you select a trade, La Rochelle, exports. Those dates, we take all the names, we do that, and then we have the coloring is from Louvain, clustering algorithm detection. And then we have the Louvain communities of product terms. And then you can see that this is a thematic map, basically. We have woods, planks of woods. We have metal stuff, fer, cuivre. And this is fil, lin, coton, so like laine, so fabrics, basically. And then we have like animals that you can maybe eat. And then we have skins. Okay, so this is an automatic bottom-up thematic ontology by using network analysis. And we think this is cool. Actually, one of my wish is to one day use the stochastic block modeling we're using on other networks as a clustering algorithm, not the Louvain one, to analyze these bidirectional generic specific terms relationships. I don't have time to explain, sorry. Final demo I will not do because that's the last slide and I don't have time anymore, but you can actually compute those networks using a long, large list of filters to fit your needs. 10 more minutes. Okay, I will finish that first. Okay, my takeaway, and then I'll demo until you die. My takeaway. What we need is to be able to change classification, because classifications are very important for social scientists. Very important. This is how we analyze. By hand. Not, by hand, mainly. maybe with some machine learning algorithm that help us, but by hand at some point. Without having to reindex, because takes a long time and this is heavy and we don't want to do that. So it's hard, but it's both on data modeling parts, which database you're going to use and how you're going to traverse this or query this, and on the user interface. Actually, we did that one, we haven't done that one, right? So even though you have a really nice graph database, if you don't have a very nice UI that requires not to have to reindex, maybe an index will be sufficient, right? So that's a very important point also. When you design a product, and especially a visual exploration product, you need to think about how your data is going to be modelized, how your data is going to be queried, how your data is going to be written, at which frequencies and by who, and which visual models you're going to use. And once you've done that, you know which database you have to use. Hard. Of course, having graph database with, important point, with a documentation page about hyperH can help you. And so as Neo4j actually helped me when I was in despair. Okay, this is my merci. My merci to you, but also to those guys. Those are the economic historians. Pierre Javet is a historian part. He actually did all the classification by hand, not all. The first three more important. Louis Charles and Guillaume are our colleagues on this project about studying this. So if I have some demo time, let's demo then. Actually, I was hoping not to have to do that because I'm not sure about my data. So the location networks, yeah. Remove this filtering time. So here I'm looking at grouping classification because country names are also classified. I just put that on the carpet. I only want local sources. I want only trading goods with Canada, and I want total value, import plus exports. And this is the network we have. Of course, it's a sigma, so you can, voila, we can do that. We can do that also. Okay, that's pretty cool. If you're lost, use this. Cool. Oh yeah, that's really nice also. I mean, visually you need to be able to choose which threshold on the labels. So which, now we have much better, but we haven't implemented it. You can choose how many labels are going to be displayed and which size they will take, which is really important. You can export as a Gephi file. No, it's a CSV, but you can import it in Gephi still. And then the product networks, here we are. Okay, but I will do the Canadian one, just to, so I choose here the Canada's, the Canada classification, local sources, only Canadian, up, total, everything, please. And voila. And then we have one community which is all about moru, codfish, which is like séché, dried. But we also have like skins. Skins were really important trade materials from Canadian, inland. Actually, we have skins of squirrels. Yes, this is squirrels in French. Caribou, vison, loutre. But, okay, you can see we have a level of details in the last nodes. Yeah, well, I think I'm good with that. In the website, you have three different visualization time series. So projecting through time, projecting through space, projecting through semantic. We have the metadata that helps you out knowing which data we have when. The classification I showed you. This is a complete list of sources we've used for archive people. And glossary, okay, because I mean it's a bit complicated, so we have this kind of, sorry, of a lexicon of different French names, sorry, French product names, and explaining you what that is. That's it. I'm good. If you have any question, we will be very happy to answer them.
Thank you so much. Any questions for Paul? Please ask the question. So, up to you how you want to. I would like to know, how did you digitize all the historic documents?
Okay. Digitalization, there's two steps. Taking pictures first. So researchers goes into the archive with a camera and take pictures of all the pages. Put them into an hard drive, then go back in the lab, and then here you have two paths. One path which is like hiring a transcripting company, which will do that for you. So you send them pictures, they send you back a transcription in Excel sheets. So the other path is hiring interns to do the same. And actually, this path is usually used after the subcontract company to check. Then we have Excel files. So those Excel files then are converted into CSVs, and so CSVs are put into a GitHub repository. And then from there, from this GitHub repository where all the data is versioned, we compile the data to build the Neo4j database, the GraphDB folder, which we then have a continuous integration system, both on code and on data. So if I push my new data on a branch on the GitHub repository, the prod server will reload a new version of the data. Yeah, well, about OCR, this is the part I haven't done anything. So that's my partner, Loic Charles, who did that. And I think maybe the transcription company did use some. But remember, ta-da! So my 2 cents about this. There is really interesting new technologies to do this kind of OCR based on machine learning, where the transcriptor person who needs to know how to read this, I can't, right? So it's like paleoautograph, I think the name in French. Those guys need to train a model to recognize that first the structure, it's column-based, there is those brackets, those are numbers, and actually we want those numbers to sum up because sometimes they don't sum up. They should. So yeah, there is one, I've seen a paper recently about, I can't remember the name, but I can share you. There is one piece of software really nice to do that. We haven't used it. Yeah.
First question, what is the size of the concurrent matrix? And then how do you try to extract an embedding from it? Like some conclusions about confused embeddings or forced embeddings?
Okay, so here, 2 things. So the first question is like, what is the size of the co-occurrence network? And second question is, do we extract embeddings? Sorry. Okay, so first question about the size. The worst you can do is working with the sources, which I think doesn't work for some weird reason, but we're going to try. And this gives you a huge network. Voilà, this is... Voilà, ça marche pas. I don't know why. It should. But okay, the second most important network is like we have 27,000 product names. And this will end up with embeddings, I don't know what you're talking about. I will be really happy to talk about this. I don't know what you mean by exporting embeddings. But what is for sure, you can extract the network from here, and then you do any fancy network algorithm techniques on your preferred softwares. But you can still see it if you're patient enough. And that's a big network. I think we can say that's a big one. We should have like the number of nodes and everything, but I don't know, it doesn't show.